Section. Introduction. We're going to talk about the evolution of large language models, LLMs, and their ability to generate meaningful text. Over time, these models have become better at creating coherent text, but they often make mistakes in their initial outputs. Some researchers have suggested that these errors can be corrected through a process of iterative refinement. This method has shown promise in various tasks like generating dialogue responses or reversing sentiment. However, it hasn't been as effective when it comes to mathematical reasoning. Previous studies have also highlighted the difficulties LLMs face when trying to identify errors in reasoning tasks. We believe that creating models that can consistently evaluate and correct their own mistakes would be a significant step towards developing more reliable language models. We've observed two datasets that involve multi-step reasoning and found that self-refinement doesn't always improve the initial outputs. In fact, it often makes performance worse. On the other hand, fine-tuning language models usually enhances their performance on a specific task by helping them better adapt to the task's objectives. We can also train smaller models on LLMs data to improve their performance. This could be a cost-effective alternative to using LLMs for a specific task. This observation led us to consider training a smaller model to decide when to refine, while a larger model performs the actual refinement process. In our research, we propose a refinement approach called ART: Ask, Refine, and Trust. This method involves 3 stages. A. Determining whether the initial output needs refinement by asking a series of questions, ask. B. Refining the output based on this evaluation, refine. And finally, C. Choosing either the refined result or the initial prediction, trust. We've tested ART on 2 multi-step reasoning tasks, mathematical reasoning and question answering, using models of different sizes. We found that a much smaller model, trained to decide when to refine, can outperform a model that's 10 times larger in a self-refinement setup. We also evaluated the trade-offs between cost and accuracy when training a smaller model with ART to make a refinement decision for a pre-trained LLM versus fine-tuning the LLM. In many cases, ART proved to be a cost-effective alternative to fine-tuning LLMs. Finally, we found that our trained models, Asker and Truster, can work with a wide range of LLMs without needing any additional modifications. There are strategies that use intermediate computation to solve reasoning tasks, such as chain of thought and sub-question decomposition, which have proven to be very effective. Most LLM refinement techniques use one of these 2 strategies or sometimes a combination of the 2. We propose to train a separate, much smaller model to make refinement decisions and later decide whether or not to trust the refinement over the initial generation. This approach is not limited to prompting-based solutions. We also train an expert model to verify each reasoning step by asking relevant questions. This differs from previous work that only dealt with hallucinations in the form of directly stated factual inaccuracies. Our work is similar to distilling reasoning skills into smaller models. However, instead of teaching smaller models to reason, we train smaller models to ask questions to verify the reasoning and decide whether the reasoning is correct. In summary, our proposed methodology, ART, Ask, Refine, and Trust, involves a trainable pipeline for refinement. Given a query and an initial prediction generated by the LLM, ART determines whether the initial output needs refinement, performs the refinement based on this evaluation, and finally chooses either the refined result or the initial prediction. Section Summary. In this section, the authors discuss the limitations of self-refinement in improving the initial generations of large language models, LLMs, for tasks like mathematical reasoning. They propose a new approach called ART, Ask, Refine, and Trust, that involves training a smaller model to determine when to refine the initial generation, resulting in improved performance compared to self-refinement. They also demonstrate the cost-effectiveness of using ART as an alternative to fine-tuning LLMs and show that their trained models can work seamlessly with different LLMs without modifications. Section. Initial Prediction. We start by making an initial prediction. Given a task query, which we'll call X, our language learning model, LLM, denoted as psi, generates an initial prediction, which we'll call Y. This is done by applying the model to the task query, so we can say Y equals psi of X. For models that have been pre-trained, we enhance the task query with a few examples of the task, which we call few-shot prompts. However, for models that have been fine-tuned, we provide the task query directly, without any examples. Because the tasks often require multiple steps of reasoning, where each step helps the model get closer to the final answer, we use two main methods for initial prediction. These are the chain of thought, COT, and sub-question decomposition, decomp. Once we have an initial prediction, we need to decide when to refine it. If we try to refine every sample, it often leads to worse performance. So, we train a model, which we call the asker, to determine whether a prediction is correct or not. We then only refine the samples that the asker is unsure about. Before a smaller model can decide whether an answer is correct or if it needs refining, it's important to align the model with the specific knowledge required for the task and the expected outcome. We fine-tune the smaller model in the style of COT, using intermediate steps with the final answer. We then create a dataset to train the asker model. We use the LLM to generate K predictions for each example in the training set, and label them as either yes or no for refinement, based on whether the prediction was correct or not. If the asker predicts yes, meaning refinement is needed, we use the LLM to refine the output. This is done by taking the input and the sub-questions from the asker model. We also provide additional facts to the model during refinement, if necessary. Finally, we need to decide whether to use the refined output or the original prediction. We train another model, which we call the truster, to make this decision. The truster takes two candidates, the original prediction and the refined output, for the task query and decides which one to prefer. However, in 80% of cases, the final answer from the refinement and the initial prediction were the same. Our goal is to train the truster to identify the correct final answer, not just a particular style of reasoning. We test our refinement strategy, which we call the ART refinement strategy, on two multi-step reasoning tasks. These are the GSM-8K and Strategy QA tasks. The GSM-8K task is a grade school math word problem task, with a training set of 7,473 samples and a test set of 1,319 samples. Each problem requires 2 to 8 steps to solve. The Strategy QA task is a question-answering benchmark that focuses on open domain questions, requiring reasoning steps to solve. It consists of 2,290 training examples. Section Summary. The initial prediction is generated by the language model, LLM, based on the task query, either with or without examples. To determine when to refine the output, an asker model is trained to decide if a prediction is correct or not, and only uncertain samples are refined. The refinement is done using the LLM and additional facts if available. Finally, a truster model is trained to decide whether to prefer the refined output or the initial prediction, based on a dataset of preferred and non-preferred pairs. The ART refinement strategy is tested on two multi-step reasoning tasks, GSM-8K and Strategy QA. Section. Experimental Setup. In our experiment, we utilized popular and high-performing base models such as Llama 70B, ChatGPT, and GPT-4. We then fine-tuned different versions of the Llama model using the GSM-8K and Strategy QA datasets. This fine-tuning process was aimed at developing the asker model, which is designed to ask pertinent questions and decide when to refine its responses. We also fine-tuned the Llama 13B model to create the truster, which chooses between the original and refined output. During testing, we used all pre-trained and fine-tuned Llama models with a method called greedy decoding. To gather diverse training data, we used different temperatures and set a parameter, K, to 5 to generate 5 predictions on the training set. All of this training was conducted on a cluster of high-powered GPUs. Our results showed that self-refinement, while beneficial in some cases, can sometimes lead to poorer performance. However, when we combined refinement with the trust module, we consistently saw improved performance. This underscores the value of our proposed ART methodology. We also found that training an asker to decide when to refine outputs was highly effective. For instance, a smaller model like Llama 7B outperformed larger models like ChatGPT by over 2 points. The Llama 13B model improved this by over 4 points. This trend was also observed when comparing refinements with the self-refinement capabilities of Llama 70B. Finally, using the 70B model as asker further improved the results. The results followed a similar trend for the GPT-4 models, where both the 7B and 13B models improved the results over the initial generation by about 2 points. Our proposed strategy, ART, improved the overall performance of ChatGPT to 82.18 after refining with a single pass, which is similar to the self-consistency score of 3 samples. The results on Strategy QA followed a similar trend, where a 7B model improved the refinement score by 1 point for Llama 70B and over 3 points for ChatGPT. The gains were larger for the 13B model, where the performance improved by 3 points for Llama 70B and 5 points for ChatGPT. This clearly demonstrates the importance of asking questions for refinement decision-making. Section Summary. The experimental setup involved using popular and high-performing base models such as Llama 70B, ChatGPT Turbo, and GPT-4. Fine-tuned variants of the Llama model were trained on the GSM-8K and Strategy QA datasets, and further trained to create the Asker model for asking relevant questions and deciding when to refine. The Truster model was also fine-tuned to determine whether to trust the original or refined output. The combination of refinement and the trust module consistently improved performance over the initial prediction, demonstrating the effectiveness of the proposed ART methodology. Additionally, training an Asker model significantly improved performance compared to self-refinement strategies, highlighting the importance of asking questions in the refinement process. Section. Don't always trust refinement. We found that it's not always best to trust the refinement process. As shown in our main table, a trust module can be useful in determining whether a refinement improves or worsens the initial prediction. We've trained a model, which we call the truster, to rank the initial prediction and the refined output, and then decide which one to choose. Our truster model, named Llama 13B, has achieved an accuracy rate of 64.24, which is 4 points higher than the baseline of 60.43. This is comparable to the accuracy of the pre-trained Llama 70B model. We've seen similar improvements in the chat version, where the accuracy increased by almost 5 points over the baseline method, from 59.55 to 64.40. We've also seen improvements with the ChatGPT model, where the Turbo model improved by about 4 points over the baseline, from 78.89 to 82.64, and about 7 points over the previous best method, self-refine, from 75.10 to 82.64. However, the gains for the GPT-4 model were minimal, possibly due to the already high performance of the GPT-4 model. But even here, the truster improved the performance to 94.08 from the previous best refinement score of 93.10. For the Strategy QA dataset, the trust module didn't prove to be very helpful, with performance similar to the refinement scores. This suggests that it's difficult to train a truster on fact-based datasets, as it's hard to rank two pieces of factual information without knowing the true facts. When it comes to the cost of fine-tuning models versus using ART-based refinement, we found that training a 13B model as a truster is 10 times cheaper than fine-tuning a 70B model. Even with two trained models as Asker and Truster, ART is still 5 times cheaper. Moreover, fine-tuning often makes the model narrowly specialized to the trained dataset, reducing its general in-context learning performance. This doesn't happen with a pre-trained model deciding when to refine using our proposed framework, ART. We also found that training the Asker to make only a binary decision of yes or no to refine, without asking the relevant questions, resulted in the Llama models always trusting the predictions and never deciding to refine them. However, asking questions leads to better refinement decisions. We compared the performance of the selection module of the LLM, self, versus our trained truster for the GSM-8K dataset and found that the trained truster can better assess the errors made in the predictions and asks the model to revert to the previous generation more often, leading to superior performance. Determining when to refine is an important part of the refinement pipeline, as always refining can lead to worse results. We found that always refining can hurt the overall performance and is worse than the initial prediction. The best results seem to be achieved with a balance of refinement, around 30 to 35% of the time. We also explored whether the Asker could be trained on its own output. Surprisingly, we found that an Asker trained on its own data can make better refinement decisions than LLM's self-refinement. However, as expected, training on pre-trained model data proved to be more beneficial in deciding when to refine. For ChatGPT models, an Asker trained on its own data performs similarly to one trained on Llama 70B models, as both data distributions are different from the ChatGPT test distribution. Section Summary. The paper introduces a trust module called Truster that determines whether the refinement improves or degrades the initial prediction. The Truster model achieves higher accuracy compared to the baseline method, demonstrating its effectiveness in decision-making. Additionally, the paper highlights the importance of asking questions for better refinement decisions and the significance of the Truster module in assessing errors and selecting the previous generation for improved performance. The study also emphasizes the importance of determining the optimal refinement percentage, as always refining can lead to worse results. Finally, the paper explores training the Asker module on its own predictions, which surprisingly yields better refinement decisions than the self-refinement approach. Section: Can ART methodology be extended to SOTA models? Can we apply the ART, ask, refine, and trust approach to state-of-the-art SOTA models? We decided to test this by fine-tuning two models, one with 7 billion parameters, 7B, and another with 13 billion parameters, 13B, using the same training strategy as the Asker models. We then compared the results. We found that the SOTA models, thanks to their additional training data and superior mathematical reasoning abilities, were able to evaluate predictions more effectively. This led to an overall performance improvement after refinement, 62.31 versus 61.33 for the 7B model and 64.06 versus 62.74 for the 13B model. These models also performed better with fewer samples, about 27% fewer samples for the 7B model and 25% fewer for the 13B model. This suggests that superior mathematical reasoning can help to better evaluate predictions, leading to fewer uncertain samples for refinement. However, because the SOTA models were trained on over 250,000 samples with rejection sampling, it wasn't feasible for us to run all experiments on this large dataset. So, we stuck to using llama models for all of our experiments. We also wanted to see if the entire ART pipeline could be learned in one go, rather than training individual models for each step. To test this, we trained a llama 13B and 70B model over the entire sequence, all in one go. However, we found that the all-in-one-go approach, represented in green, performed worse than fine-tuning, represented in orange, for the LLM. This shows that generating the entire sequence is a more challenging task for the LLM than individual components. From our experiments, we made several key observations. 1. ART allows smaller models to make better refinement decisions than LLM self-refinement. Smaller models trained to make a refinement decision can outperform a much larger model in self-refinement style. 2. Asking questions before refinement is an effective way to verify the quality of the generations and allows the models to make better refinement decisions. 3. Smaller models' refinement decisions are a cost-effective alternative to fine-tuning LLMs. The refinement decision of smaller models combined with a pre-trained LLM performs similarly to a larger model when fine-tuned. This saves a lot of computation required to fine-tune a larger model and preserves downstream performance on other tasks. 4. Expert models can make better judgments about refinement. Larger models, Asker 13B performs better than Asker 7B in all cases, show that better models can make more informed decisions about when to refine. 5. Trained models outperform llama models of similar size. A trained smaller Truster model can rank the results better than the self-selection version of LLMs.